So today topic we will discuss the design based on the frequency response method, and as frequency response indicates that we are going to find out the response for a sinusoidal input for any given linear time invariant discrete time systems. In this case we are discussing discrete systems, so therefore even like we have designed frequency response methods for continuous time systems. Similarly, we will be discussing for discrete time systems the frequency response method, and so the signal or the input that is required here is sine omega t. Okay, so let us see that if u of t is our input signal, which is given as sine omega t, and let us suppose that x of t is the output signal. Let us see for any discrete system, this is the input signal. So in this for frequency response method, when you are dealing with sine omega t, it has got a magnitude and frequency and phase angle. Therefore, that is what we have to discuss here, finding out magnitude and frequency. Therefore, now we will see what is the response first. Then we can go for the frequency response methods. We have various number of frequency response methods, and the response of a linear time invariant discrete time system. We are going to see any stable system we will consider and try to find out the frequency response of that system. And we will also go with an example of how to find out the response of this linear time invariant discrete time system when the input signal is the sine omega t, a sinusoidal signal, and what is the output x of t. Output signal can be of this sort. For example, let me say a sine omega t plus theta can be this. A is something different from the magnitude of the input signal, and theta is some other variable. Here theta is 0 for input signal, which we will consider to be 0, and let us see we are getting some output phase angle where theta is the output phase angle. So we will have to find out a and theta. So this is the aim of our topic as such. Therefore, response of a linear time invariant discrete time system is what we will have to discuss now. For that, we will see, let us say u of t is our input signal, which is sine omega t, and this sampler with sampling period capital T, and therefore we will be having u of kt. Therefore, this can be sine omega kt. Okay. When this signal is applied to a stable linear time invariant discrete time system. A stable linear time invariant discrete time system, and we are going to get the output as x of t, or you can also call it as x of kt. In fact, we are bound to find out the steady state value of this x of kt. The steady state value. Here we have the response consists of two parts, which is the transient response and the steady state response. Transient response during the initial start of the period, that our output response you will be having these transients, and these transients die out after a certain period, after settling time. Therefore, beyond which we are going to get the steady state value. Steady state of x of kt, you can call it as x ss of kt. So this is what we are going to find now in terms of magnitude and phase angle of the system. Okay. So let us say by definition you can say that, and g of z is our plant or any system, any stable system that we have considered. Okay. Now based on this, if u of t is equal to sine omega t, u of kt is equal to sine omega kt. U of kt is sine omega kt. Okay. And this is g of z. Now when you apply z transform to this, what is the z transform of u of kt? z transform of sine omega kt, we have this as z sine omega t by z minus e power j omega t into z minus e power minus j omega t. This is our z transform of sine omega kt. Now based on this diagram, let us say if we are going for z transformation here, we have x of z, z of z and u of z, and this can be termed as u of z. Okay, so u of z is this term. Therefore in this diagram we can say that x of z, from the diagram we can say that x of z is equal to g of z into u of z, and we will have to remember that g of z is the stable linear time invariant discrete time system of the plant. It is a stable system. A stable system will have poles and zeros, and based on that we can go for this. Therefore x of z. Now the output x of z in terms of z transforms, we will be having what is u of z here, g of z into z sine omega t by z minus e power j omega t into z minus e power minus j omega t. So upon partial fraction expansion, partial fraction expansion method, we can go for x of z is equal to z of z into z sine omega t by z minus e power j omega t into z minus e power minus j omega t. I just replace this here, and with this you can say that some constant a into z by z minus e power j omega t plus a bar into z by z minus e power minus j omega t plus terms, because we have these two in the denominator, and g of z is a plant which is a stable linear time invariant discrete time system. Therefore it will have some poles. So terms due to poles of g of z. Terms due to poles of z of z. Now consider this equation. Now considering this equation and multiply throughout by z minus e power j omega t by z. The entire equation. So when you multiply the entire equation like this, then what is the left hand side that we are going to have? G of z into z and z gets cancelled, and z minus e power z j omega t is cancelled. Therefore the left hand side becomes g of z into sine omega t minus z minus e power minus j omega t. This entire multiplication of this factor and this factor, we get this. Therefore, and multiplying throughout, you get this is also multiplied here, z by z, and so I'll have a plus a bar into z and z is cancelled, and we are left over with z minus e power j omega t by z minus e power minus j omega t plus z minus e power j omega t by z into terms due to poles of z of z. Now let us substitute z with e power j omega t in the above equation. Okay, z is equal to e power j omega t. if we substitute here, what is that we are going to get? The left hand side I will leave it as such, because z of z is a system where we are substituting, is a stable system, and we are substituting z is equal to e power j omega t, and hence I will have this sin omega t by z minus e power minus j omega t, where z is equal to e power j omega t. We will look into this at a later stage. First we will go to the right hand side. A plus a bar, when you substitute z is equal to e power j omega t, then the term becomes 0 into 0 plus again z is equal to e power j omega t minus e power j omega t. This is also 0 into terms due to poles of 0 z. So this and this gets cancelled. Right. So you don't have the second term and the third terms of the initial equation of this system. Therefore, what is A for us now? A is g of z. A is equal to this part into sin omega t by z minus e power j omega t, when z is equal to e power j omega t. Now this is what we have obtained. Now let us see what is that part. Now A is equal to g of e power j omega t into sin omega t by z is this is e power minus j omega t, e power j omega t minus e power minus j omega t. Now what is this one? E power j omega t is cos omega t plus j sin omega t minus cos omega t minus j sin omega t. Okay, c minus c, right? So these two gets cancelled, plus js minus of minus plus js 2j sin omega t. So the denominator becomes 2j sin omega t, 2j sin omega t. Therefore these two gets cancelled again. Therefore what is the value of A for us here? A is g of e power j omega t by 2j. So this is what we are having as the value of A. Right. Now when you have A here, what is A bar? It is the complex conjugate of A. Therefore minus 2j. J becomes minus j. Therefore g e power minus j omega t. This is A and A bar. Now these are the only two terms which we will have to find out in the initial equation that we have got after applying partial fraction expansion method. Right. So when we are having this, what is the equation that we are going to get? A is, let us discuss about g of e power j omega t. G of e power j omega t. M is the magnitude of this is given by m is equal to modulus of g of e power j omega t, because g of e power j omega t is nothing but the stable plant which we have considered when z is equal to e power j omega t. That is, we are converting the z domain into a frequency method, frequency response method. Therefore, in order to find the frequency response method for any given stable system, we will have to replace z with e power j omega t to get the magnitude. And similarly, the angle phi is equal to angle g of e power j omega t. We know that g of z is a complex is a system which has complex values, right? So complex values will have both magnitude and angle, phase angle. Therefore, we are going to get these two values, magnitude and phase. Okay, so this is what we have obtained. And after which, to get this values, we need to find out once again rewrite the x of z. X of z is equal to u of z into g of z, where we have got a into z sine omega t by z minus e power j omega t plus a bar z sine omega t by z minus e power minus j omega t plus this is x of z, or u of z into g of z after multiplication, after partial fraction expansion, plus terms due to poles of g of z. This is nothing but x of z. Right. So what is a that we have got? It is nothing but g e power j omega t by 2j z sine omega t by z minus e power j omega t minus g e power minus j omega t a bar is this one by 2j z sine omega t by z minus e power minus j omega t plus terms due to poles of g of z. This is our x of z. Okay, so this is what we are going to do. And since all these are complex values, you can just combine all these values and get the value of magnitude and phase angle of this system. Magnitude of phase angle of this system. Therefore, we are going to get, after multiplication or after inverse z transforms, we are going to have x of kt, which is nothing but a into sine omega kt plus theta. Omega kt plus theta. We need to find out what is a and what is theta in this case. Now let us see an example. Sir,